Okay, so for those of you who have questions about the coordinate zones, this is what our coordinate zones for the state plane system look like in the state of Wisconsin. So the black lines that are on here, these jagged black lines, are the best fit coordinate zone for the central zone. Okay, so central zone is between these big black lines. But they're based on the north part of the central zone being 45 degrees 30 minutes. That's where the scale factor is 1. And the south end of the central zone where the scale factor is 1 also is 44 degrees 15 minutes. So those are the extents of the central zone. The north extent of the north zone not shown on here. So it's outside of the state of Wisconsin, so it's not really relevant for us. We don't really care. What was that?
It's in Canada?
Yeah, it's in Canada, eh? And then the south zone, same thing. The south zone's extents are down into Illinois, so they don't show the extent of the south zone. So this will give you a better idea where our zones are and what defines them. Now this pink line going up straight up through the middle, that's our central meridian for the state of Wisconsin. Runs north-south like that. Our initial point is right down here by my finger. That's where our initial point in the state of Wisconsin is. So that's how this zone is, or these zones are defined, is based off of these parameters. So that just gives you a little idea, better idea of what we're working with the south zones, or in central zones. Okay. Now, next thing we're going to tackle here are these assignment 2, the lat and long problems. I'm going to do a couple examples. Here's what the assignment looks like. So for the first one, I give you latitude and longitude, and I'm asking you to convert those to state plane coordinates for those first 2 problems. Okay. For the next 3 problems, I'm giving you a state plane coordinate for 4 and 5, and I want you to tell me where those locations are by using Google Earth. So you'll after you compute your latitude and longitude, you're going to take and plug that into Google Earth, your latitude and longitude, and have it drop a place mark where I'm asking you to look. Both places are very notable spots, so you'll notice it as soon as you see it via aerial photo. You'll know exactly what it is. So we're going to work on the first one we're going to do is the latitude longitude to the grid coordinate, the state plane coordinate. So I'm not going to do one of these example problems. The example problem I'm going to do is off of the coordinate, the state plane coordinate tables. I'm going to basically do one of these samples that are here. Okay. I'm basically going to do both of these samples that are here. We're just going to go through the math of how they got there. Okay. They sort of do it up here and show you how to go through it, and basically that's all we're going to do. We're going to follow how they do it on here, but in my way. If you want to do it a different way, you can. That's fine. I don't care. But this is the way that I tackle these problems. So the first one we're going to tackle is from latitude and longitude to grid coordinate. All right, so let's explain this whole thing first. This here, I'll try to explain this, what all these little things mean on here. And hopefully I get my Greek letters right. If anybody's stronger in Greek letters than I am, I appreciate letting me know what things are. All right, so this number right here with the F is it's the flattening. That's the rate of flattening for the grid calculation that we're going to be doing. So this is flattening. That's the F. Okay. We're going to call this phi. I think that's the Greek letter for that. This one is lambda. And these are each phi. Okay, it tells you what they are. The extents of the parallels, the standard parallels for the coordinate system. So phi sub b is the latitude of the grid origin. So that's where the grid system's origin is coming from for the central zone. Is 45 degrees, 50 minutes. The longitude of the origin and the central meridian, which we just talked about on that map, is 90 degrees. If you looked on that map, it showed 90 degrees. Here, 90 degrees. This is our central meridian. Then the southern standard parallel is at 44.15. So we're in the central zone. The northern standard parallel is 45.30, which I showed you on that sketch. So these are the parameters for the central zone. So the easting origin is at 600,000 meters. That's the easting origin. The northern origin, which you're going to see, this is really nice that they have it at 0 for us. It's going to come into our calculations. It'll be one less number to have to write down. So the northern coordinate origin is 0 meters. Okay? Alright, we're going to call this is gamma. Not your grandma, it's gamma. And we're going to take and solve for this. We're going to solve this one first. Okay? So we're going to do the Lambert coordinates from geodetic positions. Okay? So grid coordinates, central zone coordinates to geodetic positions. Or from geodetic positions, sorry. So we're going from lat long to northern easting. That's what they're showing here. Lat long, northern easting. Okay, so we're going to use this one as an example. So when I talk about these different items in here, that's what we're going to use in our calculations based off of this sheet. So you can go back to this sheet when you're doing your calculations to remember what different variables mean. So what we're going to do is we're going to use these formulas right here to calculate it. Okay? When you go to do your homework, use these formulas on here, and this is exactly what I'm going to use. So maybe have this up on your computer so you can reference these as I go through and you know where they're coming from.
Where is that located?
This is located under coordinate projection tables, Wisconsin State Plain Zones, and we're in the central zone. So you click on central zone, and there it is, right there. Okay? This is exactly what I'm talking about.
Go ahead.
Back at her. Okay. So let's, I'll slide this over to the side. I'm going to try to make them so they're together in here. Okay, so for this first one, we're going from lat and long to coordinates. Northern easting. Okay? So Lambert coordinates from geodetic positions. So lat and long to coordinates. Alright, so we know that our latitude is 44.52:30. 44 degrees, 52 minutes, 30 seconds. And our longitude is 90.30.00. Longitude, 90 degrees, 30 minutes, 00 seconds. Okay, so that's what we know. Now, the first thing we want to do here, is we're going to want to solve for gamma. Here, this equation, nice long equation here, gamma. Okay, so let's write that out. So if I do gamma equals lambda Cm minus lambda times the sine of phi r. Okay, so that's the first equation that we're going to use. Let's talk about each of the variables in there. So this lambda Cm is a constant that's given in the variables of our central zone. Okay, so lambda Cm is 90 degrees. Okay, that's the longitude, origin, and central meridian of the coordinate projection. So lambda Cm is 90 degrees off of this sheet. So we're going to throw that in there. 90 degrees, 00 minutes, 00 seconds, minus our regular lambda. Okay, the regular lambda on this sheet why am I not seeing it? 90, 30. Oh, right here. This lambda right here. This is lambda. Okay? 90, 30. So the longitude is lambda. Okay? So it's 90 degrees, 30 minutes, 00 seconds. Okay? So that was the longitude given to us. So this is all this is the given information, right? Lambda. I should probably write lambda up here. Okay. And then we times it by the sine of phi r. Well, where is phi r in here? Well, okay, so if we look right here, it tells us that this L, this value right here, is equal to the sine of phi r. This value. So it's a constant. They give it to us. They already figured that out for us. So phi r is this big long number here. So, or the sine of phi r is. So 0.705576614,409. That's that big long sine of r, or phi r. So that's, they give that to us here. Phi r. Okay. This will be the case on every one of these problems you do. These variables will all be the same. Well, not be the same. They'll be different for different coordinate projections, but these items don't change for the central zone projection. Okay, so our gamma is what? Now this should be displayed, this gamma should be displayed in, you can show it in decimal degrees, but what it's coming out as is degrees, minutes, seconds. Yes? No, you don't have to sign it at all. It's equal to that. So that number is the constant. That is what sine of phi r is what that's saying. That 0.7055766 is the sine of phi. That's what the answer is if you sine phi. Okay? So that's what the answer is.
Do we keep it negative?
What was that?
Do we keep it negative?
Yes, keep it negative. So if the answer comes out negative, you keep it negative. You preserve the sign. Okay, so whoever gets the answer for gamma, let me know.
In decimal?
Sure, give it to me in decimal degrees.
Negative 0.35278831.
Okay, I'm going to hold it out more because in geodetic calculations, as long as you're calculator gives it out to, write it down. Because it'll make a difference. Okay, so what is this in degrees? You may give me the degrees for that? 10.0379. Okay. So that's what it is in degrees. But as we go through the calculations, we're going to use it in decimal degrees. All right. Okay, so we just figured out gamma. So in our line of equations over here now, that's the next thing. After we found gamma, we can find the E. So this is the easting we're going to find. The E is for our easting coordinate. So we know what R is. They give us R. Okay, we're going to have to probably find that from the latitude tables, the radius at that point. Okay, so we're going to have to go out and find R.
Don't they give it to you down below?
Yes, they did. They were nice and gave it to us. We could have went in the tables and found it. They gave it to us here. So we can find it in the tables also. In here, R. That's how you're going to have to do your calculations. You'll have to figure out R from here. So, but they give it to us here. But R, when you go to find it, you're going to have to find your R for your latitude that's given, okay? So 44, 52, 30. I go 44, 52, 30. 44, 52. I'm going to end up doing a proration between these two numbers here. To figure out my R value. Okay, so that's where the proration comes in. You have to basically figure out the difference between these two and then figure out what your R value is. So the proration between these two with my degrees, minutes, and seconds comes out to be R right here. This R for this problem. So the next thing we're going to solve for is E. So E is equal to, from the formula, R sine of gamma plus E sub R. Okay? So R we find from our tables. Gamma we just found. And E sub R is the easting coordinate given to the projection. That's the E sub R up here. Okay? So E equals the R from our tables, and they already figured that out for us, 641.6219.385. This is all in meters now. Sine of our gamma, 0 degrees, 21 minutes, 10.0379 seconds, or you can just throw your decimal degrees in there, it's fine. Plus our E sub R, and that's 600,000 meters. Okay? So E is equal to what? Now this value that E is going to give you when you do this calculation is in meters. Well, I want your answers in feet. So you're going to have to convert from feet to meters. Or from meters to feet, sorry. From meters to feet. There's right now.
Uh, 560,493.571977. Kind of.
All right. So what is it in feet then? Meters to feet.
0.38.
3.28 equals 1 meter.
But make sure you take it out far enough. It's 3.2808333333. Make sure you take it out far enough, or else you're going to have a rounding error in it. So 3.28. So in 1 meter it equals 3.280833 repeating. Okay, feet. So what is my footage? What's my easting coordinate in feet?
1,838,885.99219.
992. I'll take 992. Okay. Feet. All right, so there is my easting coordinate. Okay? Now we have to figure out our northing coordinate. So it tells us how to do that right here, or what that formula is. The northing equals RB. Okay, RB is a constant here. That's the radius, the mapping radius of the grid origin. It's right here. So RB minus R cosine of gamma plus NB. Well, what the heck is NB? Well, this is where it gets nice. We don't have to add that into our equation. So RB is this mapping radius for our grid origin. That's given. So 6531967.9926 minus R, which is given to us here. And that's from the tables again. R is from the tables. 6416219.385, all in meters, times the cosine of gamma. We figured out gamma already. It's right here. And that is cosine of 0 degrees, 21 minutes, 10.0379 seconds. And then plus NB, which, if we look in the table here, NB is 0. So we don't have to do anything with that, just plus 0. Okay? So that's how we're going to calculate our northing. This is, again, going to be calculated in meters. So we're going to have to convert to feet. So can someone give me what the meters calculation is there for our northing? $115, comma 870. Okay, that's in meters. Let's put it in feet. $929 feet. Okay, so that is our northing that's our northing. So this is our easting, northing in feet. So we just solved our northing and eastings from a lat and long for the in central zone coordinate. Okay. Any questions on that one? It's basically all we did was use these three equations that are shown, and we used the variables from the coordinate projection. Okay? So when I give you in your homework, you're able to use this coordinate projection. So you'll have all these variables, just know what they are. Okay? Just know that R here, this R, this value here, is something that you're going to have to go into the projection tables for and to be able to calculate. Proportion thing. Okay? And need to know how to do that.
So what's the bottom number, the negative 0.21? 10. Oh, what? Not that one. Yeah.
That here, that's gamma. That's what we figured out up here. So, okay. So the next one we're going to calculate going from coordinates in our central zone to latitude and longitude. So we're going to figure out our latitude and longitude. That's the second half of the assignment that you guys are going to end up doing. So we're going to do another calculation similar to that. Any other questions before I move on to figuring out latitude and longitude from coordinate? Right here, this, you're timesing it. In the formula, you're multiplying it by it. So, multiply it. Okay. So this is supposed to be negative here then. Make sure that's negative. I didn't have it as negative before, so. Alright, so let's tackle the next one. And you guys will be able to rock and roll on homework and get this going so that we have time. So this next one we're going to talk about is the geodetic positions from Lambert coordinates. Okay, so we're going to solve from northings and eastings and go to latitudes and longitudes. So we're going to do this problem here. That one right here. Okay? I'm going to use these numbers off of here again for an example. Okay? So we're going to go from coordinates to lat and long. Okay? So our known is our northing. If I look on here, northing is 120,000 meters, and our easting is 640,000 meters. So that's our known. Alright, so let's start with this first equation that we have down here. Slide this over a little bit. So this first equation that's here to go from geodetic positions, or northing and easting, to lat and long is the tangent of gamma equals the easting minus the easting r, which is the easting of the origin coordinate for our coordinate reference system, divided by RB, which is our mapping radius of the grid origin. That's this number here, RB. minus N minus NB. Okay, so N is the northing that we were given. Okay, this northing. And NB is the northing coordinate for the origin. Okay? So if we figure this baby out, equals E is 640.00 minus ER, which is 600,000 meters, which is our mapping radius, again, that was given on the coordinate information. So the mapping radius is 6531967.9926 minus, that's the RB here. Yep. And then N is our northing that was given to us. The northing is 120,000 meters minus NB. Well, NB is given and it's 0. So our tangent of gamma equals what? I'm going to try doing this one on my little calculator too, just to make sure. What's our tangent of gamma? Or don't just don't give me the tangent of it. Just give me what I'm looking for here. Tangent of gamma. I want that actual value.
0.6238334.
Okay, so it's 0.0062383334. Okay. So what's the tangent of that then? Arctangent, yeah. Arctangent of that particular thing.
0.357425591.
0.357425591. So that's decimal degrees right now. So if this also can be shown in degrees, minutes, and seconds. 0 degrees, 21 minutes, 26.73212 seconds. Notice that it's the same thing as what they give us here, so that's good. We have a check on this sheet. That's not always going to be the case for you guys, but for this particular problem they already gave us those answers. So our gamma here now for this problem is this value. Okay? Next step. Let's figure out R here. Our radius. Okay? So R equals RB minus N minus NB over cosine of gamma. I just put lambda in there. Gamma. This should have been gamma here too. I was putting lambda in the whole time. gamma. Well, we already sort of figured, we could have figured this out on the bottom for our calculation we did up here. Okay. So we know that that is says 6531967.9926 minus 120,000 minus 0. So that's the top. We already figured that out up here. Then the bottom is the cosine of our gamma. So it's cosine of 0.357425591. So R equals what?
6,412,092.75807.
6,412,000 092 point.
75807.
Okay, so now that gives us our radius. So, all right, at this point we can find our latitude. How are we going to find our latitude? Okay, so I want to find our latitude here. I can use this radius. Now this is where I go to my tables. Okay? And I sift through and filter down through here and see if I can find this number. 6,412,000. So 6,412,000. Get rid of that. It's between here and here. Okay? Between these two numbers. We have to do proration again to figure out what our latitude is. But this time we're prorating the latitude. Or we're going to prorate the radius, but that's going to help us find the latitude. Okay? So if I go, I look here, and at 44 degrees, 54 minutes, 00 seconds, I'm at 6,413,441.310, and then at 44 degrees, 55 minutes, 00 seconds, I'm at this radius, 6411589.253. Okay, so now I'm going to have to go figure out where this is in this location here. Okay, so what I can do is take my higher number here, 6,413,441.310, and I'm going to subtract our R that we came up with. The R that we came up with, I'm going to subtract from this. So minus 6,412,092.758. I'm just going to carry it to 3 decimal places. That's what the other one is. Okay, so if I subtract those, I come up with 1348.552. Okay, so now what do I do with that number? Give it to someone else. Yeah. Well, there's another thing in here that we're going to need to use. Okay? And that is this number right here. That number is the difference per degree in meters. Okay? So we're going to want to take that difference in meters per minute, I should say, sorry, per minute, and use that. So what we're going to do, we're going to take that 3086762 That was too close. Three zero 86762, and we're going to divide this number by that. So 1348.552 divided by that, and that's going to tell us how many seconds we have. Okay. This, what'll come out of this is how many seconds we have that we're going to end up adding to one of these or subtracting. Okay. So what is the number of seconds here for this calculation?
Uh, 43.688.
Okay. 0.688. All right. So now, actually, we should carry this out.
238.
238. Okay.
238.
2403.
You're wrong.
All right. So here, okay. So now what we're going to end up doing is we're trying to find our latitude, right? Well, we know that the latitude here, or the lower latitude always, because we're always going to add to it. Okay. So that's why we use this number here. We use the lower latitude, even though we're going between these two. So I always use the lower latitude that we're going to add this to. So if I look at that, it was 44 degrees, 54 minutes, right? Was our lower latitude. This is a 5. Now we just add our seconds. 43.688238 seconds. So that is our latitude we just figured out right there. Okay? So we just figured out half of the problem we're looking for. So the other half now, we have to figure out lambda here. Okay? So let's look at lambda now. Lambda equals lambda cm, which is given to us, minus our gamma divided by the L that was given to us. This L is the sign of phi, R. So it's this number here. So lambda equals lambda cm. So lambda cm is 90 degrees. 90 degrees, 00 minutes, 00 seconds. Minus our gamma that we figured out, which is up here. 00 degrees, 21 minutes, 26.73212 seconds, divided by the sine of phi, sub r, and that's given to us. That 0.7055 7661 4409. Okay? So gamma is what?
Is this going to be in degrees? Seconds? Yeah?
Yes.
Okay.
It'll be in degrees, minutes, seconds. So what do we have for our gamma, which is also our longitude? What do you get?
I have 89 degrees and 41 minutes.
Nope.
29 minutes?
Shoot.
36.3 seconds. That's as far as I could.
Yeah. 89 degrees, 29 minutes, 36 point. Carry them out as far as you can. 3,9603 seconds. Okay, so this latitude here, and we just figured out our longitude, so we're good there. Okay. Latitude here is a north latitude, okay, because it's positive. So we want to make sure we say north latitude, or you can put it at the end, latitude north, okay. The longitude, because it's positive, actually this is supposed to be a negative, it's not going to come out as a negative, but we know that we're in the west here because we're west of the Greenwich Meridian. So this coordinate is a west coordinate. Okay, latitudes and longitudes for us, for our purposes, are north latitudes, west longitudes. Anything in North America will be west longitudes. Okay, it just means that we're west of the Greenwich Meridian. Alright, so you just came up with the latitude and longitude from coordinates given, geodetic coordinates given, to get those figured out. Any questions on this one? I would take and change, if you can change your calculator to display more decimals, do it. The HPs, I know you can change them to show more significant digits.